Very good. All right. So I will pass over to you now, Martin, so that you can take us away with the next session. Thank you again for being here.
My pleasure. So, I'll spend the next 50 or 55 minutes or so talking about density functional theory. And if there are questions, I may not notice them if you raise your hand. So someone needs to actually jump in and yell out, but I don't mind answering questions as we go along. The outline for this talk is, this is basically, I'm giving a talk after the following break, which after the, so this will lead into Peter's geometry optimization talk that includes examples, and that leads into my own spectroscopy, computational spectroscopy by DFT talk that also includes exercises. This talk has no exercises. It's just kind of a stream of consciousness discussion with some slides to guide me about some fundamentals of DFT and things that I think about regarding density functional theory. So I'll begin with an introduction, then talk about the design of density functionals, at least what I can say personally about that. These are functionals that I've been personally involved in designing, and then broad questions about the performance and performance limitations of density functionals, which will be, and in some sense, all of these themes will go through the talk. So let's just remind ourselves a little bit. Density functional theory has a rigorous foundation through the Hohenberg-Kohn theorems and the constrained search construction. And on this slide and the next slide or two, I will try and put things in blue that are given exactly and things in red that are not given exactly. And so there is a theorem, the Hohenberg-Kohn theorem, that says we can get the energy by minimizing a universal density functional that is shown in red here, that is not known exactly and never will be. And in fact, we don't really even want to know it exactly, because if we could know it exactly, we still couldn't afford to evaluate it. And then there's the thing that differentiates one system, one material, one molecule from another, which is the interaction with an external potential, the Coulomb field of the nuclei. And you just go and minimize it, and you get left with an unsatisfying picture for what is the universal density functional. Well, it's really the minimizer over all wave functions that give rise to the electron density you're currently thinking about, as long as that electron density comes from a wave function. If you do it this way, it's guaranteed to. So since we'll never get that exactly, we're going to have to model it. And so all density functional models in some way trade off accuracy against feasibility. Here's the perfectly accurate one, and it's perfectly unfeasible. We'll discuss some perfectly feasible ones that are relatively inaccurate, and then we'll look for some compromises. And so then we'll have a model functional that will stand in for the exact one, and we'll then do that minimization, and one will then test and see whether chemical energy differences are actually reliably reproduced or not. The first piece of bad news, of course, is that the biggest piece of the energy that is not known exactly is in fact the kinetic energy. And there is no density functional yet that can do that, at least that can do that accurately enough. And therefore, all modern density functional theory abandons the search for a kinetic energy density functional in explicit form, and instead uses a reference system of non-interacting electrons, the Cohn-Sham reference. And this is where orbitals make their appearance into density functional theory. We need a wave function, a single determinant that describes exactly a set of non-interacting electrons whose density is the same as the real physical system. And this solves both of the dominant problems with true density functional theory. We will now evaluate the kinetic energy exactly for the non-interacting electrons. So this then goes from red to blue. It's gone from inexact and not yet properly solved to now blue and exact. And it also solves the n representability problem. If someone presents you with a density, how do you know it comes from a wave function? Well, now we do know. This comes from the Cohn-Sham determinant for sure. So the n representability problem and the kinetic energy problem are solved. And our total energy then is, at least for the universal density functional that is still in aggregate unknown, it's now got two exact pieces. The kinetic energy is exact, and the classical electron-electron repulsion, which is that 6-dimensional integral up the top right, that's also exact. And then there's the stuff that is non-classical that involves electron-electron interactions, and that is exchange and correlation, and that must still be modeled. But this is infinitely better because now the biggest terms the three biggest terms are exact, and we're making approximations to smaller terms, which is good. So the functional design problem in Q-Chem DFT is modeling the exchange correlation energy alone. And that modeling, well, to kind of encapsulate, what is now going on for 60 years of modeling, the idea that is attributed to John Purdue of grouping functionals onto rungs of the metaphorical Jacob's ladder is a powerful way to go. So, so the idea is that one ascends from a primordial ooze, the Hartree world, where electrons don't even have the right spin symmetry, to climb relentlessly, as progress is relentless, towards the heaven of chemical accuracy, where density functional theory can stand in for experiment and can make robust predictions. And in this last bit of the introduction, I want to sketch for you a little bit about what goes into this ladder and why it is a useful construct. So we will open the hood of density functionals just a little bit to consider what is the exchange correlation energy at each of rungs 1 through 4, and it's a 1-point correlation functional for exchange and correlation. It involves just the density at a single point, making an exchange correlation energy density. And that's an audacious thing, right? Because by definition, exchange and correlation involve 2 electrons at a minimum at a time. So the idea that you can make a somewhat useful model using just a functional of only 1 electron at a time is already remarkable. But anyway, that's what it is. And then well, this bottom rung, this can be exact for a class of systems, the class of system where there is nothing beyond simply where this descriptor is adequate. And that is the uniform electron gas, because in the uniform electron gas, the density is not a function, it's just a number. It's whatever the density is. To go beyond uniform electron gases, you need to consider non-uniformities. And if you want to keep this audacious 1-point correlation and exchange functional in terms of the density, then you should consider inhomogeneities in the density. So the density gradient would then be the simplest inhomogeneity. And those are GGAs. If first derivatives might give you something that's better, then maybe second derivatives in some form or other would be even better. So the kinetic energy density, or sometimes the Laplacian, then defines rung 3. And now it still has this same 1-point character, now involving also the kinetic energy density, or tau, at a given point in space. So rungs 1 through 3 have this 1-point character to it, and then that is abandoned at rungs 4 and 5. So at rung 4, we mix in wave function exchange. It's sometimes called exact exchange, and the reason it's exact exchange is because we know the exact wave function for the non-interacting electrons that represent the system. That's the Q-Chem determinant. So we can evaluate the exchange energy with the orbitals of that determinant, and that would be exact exchange. And the adiabatic connection tells us that exact exchange must contribute to the exact function. And so chemists and condensed matter physicists have built in exact exchange into density functionals in various ways, and that defines hybrid GGAs and hybrid meta GGAs. And then finally, one can complete throwing the kitchen sink of descriptors at the problem and allow the density functional to not just depend on the occupied orbitals, as it does if you have wave function exchange, but also to depend on the virtual orbitals. And so that would be rung 5. Okay, so that's the ladder, and I guess let's see then. What can we say about what can we say about the performance on the ladder? Well, here's just picking out 4 functionals representing rungs 1, 2, 3, and 4, and you can see that the RMS error here drops precipitously as you go from rung 1 to rung 2. In fact, it was really in the mid-1980s that density functional theory became interesting for chemistry with the advent of usable GGAs like BLIP to begin with, and then PBE later on. Then the meta GGAs, represented here by the MO6-L functional, and this is, by the way, data something like 200 atomization energies. You can see it's a statistical improvement. And then here's a good hybrid density functional, MO6-2X, and you can see further improvement. So basically, this, in some sense, justifies the Jacob's ladder. And I can see there's a question about local hybrids. So local hybrids, in some sense, sit really, I guess, more or less on rung 4 as an alternative to global hybrids. I won't say anything more about them today, but that is one way to do more with an occupied orbital dependence. In other words, instead of integrating over all space, actually consider the exchange energy, the exact exchange energy density at a point in space. I will say a little bit more about why exact exchange is needed in a kind of general way. And I already mentioned the adiabatic connection as its justification, but it's very good to just ask, where is a problem where the exchange functional is truly the cause of errors? And surely it's a 1 electron problem. So if we take the 1 electron problem that is H2+, then mean field theory is exact because there's only 1 electron. And normally good functionals like GGAs go disastrously wrong as you stretch the HH bond in H2+. And since there's only 1 electron and the kinetic energy is exact, this is clearly a defect of the exchange interaction. It's not canceling properly the classical Coulomb interaction at long range. You can see that the hybrid functionals do a bit better. 20% exact exchange is not as good as 50%. And you then get the idea as you go from 0% exact exchange to 20% to 50% to 100%. This is failure of the exchange functional. So this is sometimes called the delocalization error, because what you get when you stretch H2+ to long distances is not the hydrogen atom and a proton. If you did that, the energy would actually be quite close to the right result. In other words, if we constrained the density function, the density for the density functional. So this is an error that is density driven. What we actually get is 2 hydrogen 1/2 pluses. And the prediction, the outrageous prediction, is that energy is released when you go from a proton and a hydrogen atom to 2 hydrogen 1/2 pluses. That's an error of the exchange function. You can reduce that error by range separating exchange. So in other words, if this is a defect at long range, well, why not recognize that the idea of modeling exchange as a function of just 1 electron coordinate will be worst when the 2 electron coordinates that actually make exchange are furthest apart. So put in 100% long range L exact exchange and a variable fraction Cx of short range exact exchange, and use a partition of unity, i.e. split the number 1 into 2 functions that add up to 1 that are both positive semi-definite, and then you'll be able to actually do a little better. Here's a more difficult problem than H2+. It's helium 2+. It's now got 3 electrons. This is sometimes called the 3 electron 2 center bond. It's more difficult than H2+ in the sense that the GGAs do even worse. In other words, the energy of 2 helium 1/2 pluses is below the energy of the molecular ion. There's a barrier on the way out, but that's the delocalization error playing a role. The range separated hybrids don't cure it completely, but they make it less bad. So one of the limitations of DFT that, that is partly addressed by local hybrids, which comes back to Florian's question and why local hybrids are an interesting area of current activity, is that you can further reduce the delocalization error that way. What are the other errors that are evident on Jacob's ladder? Well, one is something that's left out, and that is non-local dispersion. So dispersion is the weak, uniform, attractive background that causes all matter to want to stick together. And a dispersion interaction cannot be described as a functional of the position of just one electron. By definition, it's a density-density correlation at long distance. So Jacob's ladder was not designed with the idea of dispersion, being dispersion aware, so it sort of then needs to be grafted on. And it's now common for almost all density functionals to be dispersion aware, either by adding an atom-atom potential. That's not strictly a density functional at all, but it's a pragmatic and quite effective solution, as pioneered by Stefan Grimmer, or add a non-local van der Waals functional like VV10 or VDWDF2, where the density, where there's a 2-point density-density correlation involved. And then here is just a little bit of data to drive home the fact that if you take one of chemistry's favorite functionals, the B3-lip functional, here are some root mean square errors for some data, and the same data with a dispersion correction added reduces those errors by a factor of roughly 5 or so, maybe 3 to 5. So the same functional, just dispersion corrected. So definitely one needs to dispersion correct. So anyway, so that I guess is in some sense a brief perspective on DFT. Now let's turn to the question of functional design. And here's a paper that attracted what might be called a storm in a density functional teacup about 5 years ago, claiming that DFT is straying from the path toward the exact functional. Here's a little quote from that paper. Atomic densities became closer to the exact ones, reflecting theoretical advances until the early 2000s, when this trend was reversed by unconstrained functionals sacrificing physical rigor for the flexibility of empirical fitting, said these authors in this paper, and this was the data they produced to support it. On the y-axis is error in the densities of spherical atoms and ions, and on the x-axis is the year in which functionals were proposed, and the data points are thus individual functionals. For instance, this could be two fits of the LSDA. Here could be some early GGAs, and as we march on, more and more functionals are proposed. And the point of the quote is that it seems like more recent functionals are going wrong. And actually, when I first saw this, I was kind of concerned, because actually 2008 or so was the year when my group first began publishing work on density functionals. We started trying to develop them about 3 years earlier. And that's roughly when the early 2000s, when this trend was reversed. So I was concerned. But then when I looked into the data, it turned out that all 14 of the worst post-2000 functionals were developed by a single research group. And so if one deleted those outliers, then the trend actually would look quite a bit more reasonable. But that's kind of a maybe a dig into the data. The broader theme is that DFT needs new strategies for functional development. The more complicated the functional, the more difficult it is to have a clear strategy to develop something of high accuracy and broad usefulness. So now we'll switch to the second topic, which is about the combinatorial design of density functionals, which is the effort from my group to address the question of how to better design density functionals. As you'll see, this is quite a successful exercise, and it will then lead us naturally into looking at the broader performance of density functions, or at least many density functions. And the idea of combinatorial design, which could be called survival of the most transferable in a sort of a nod to Darwinism, is that we would take a very large space of possible functionals and try and search that space to identify an accurate transferable functional that is minimally empirical. And we were able to, I mean me and a brilliant student, Nabe Marderosian, to round up 5,000 benchmark values, 5,000 pieces of data. And then we would divide that data following principles of statistical learning into a relatively small training set, a much larger testing set, and then some secondary test data. So any parameters that enter the functional will be fitted based on just the training data. And then the question of how to choose between many candidate functionals would then be based on their predictions for the test data. And then because that could lead to some selection bias, we would then reserve the secondary test data to check and see that the selection bias is not critical. The human element inevitably enters. So the weights of individual test sets, individual data points that represent energy differences, that is human defined. So this is at best supervised learning. We define the weights in order to essentially define a loss function, if you like. And in the end, total RMS errors balance the trade-off between finite amounts of trusted data versus too much dependence on the training data and overfitting. So in principle, the great merit of this approach is that we avoid overfitting to the extent possible. You can't ever be sure that you've avoided overfitting. And least empirical, well, this basically means we should choose a simpler functional over a more complicated functional, if at all possible. And so that's the idea. And we need, this is a very quick glance at the data. Don't stare at it too hard. The only thing to stare at is that the data comes in categories. There are non-covalent interactions, that's NC henceforth. And we split that into easy and difficult. You might imagine what easy and difficult is. Difficult are things that are sensitive to the errors of DFT that our choice of functional form probably can't cure. So this includes the delocalization error that I talked about. It also includes strong correlation errors in some cases. And something that's easy, conversely, should not be susceptible to those errors. Something easy is something that we should be able to describe. So NC, non-covalent, I for isomerization energies, TC for thermochemistry, those will be atomization energies, and then finally BH for barrier heights. Let's now ask what is actually inside these functionals. And so there are up to 3 different classes of ingredients here. The first class is mandatory. In black here are the 1-point exchange and correlation, the semi-local contributions that just depend on the density and maybe its gradient or the kinetic energy density at a single point in space. Then optionally comes exact exchange, and in the functionals we've developed, this was done in the range separated sense, not local hybrid, but range separated exact exchange. And then finally, a dispersion correction that's in the form of a van der Waals density functional, and we use the VV10 functional of Vidrov and Van Voorhis. And if we start by looking at the semi-local terms, if we make a GGA-based functional, it will take the form of the exchange or correlation energy at the LSTA level, then multiplied by an inhomogeneity correction factor that is contained inside this this summation, and this is essentially like a little Taylor or Maclaurin series in a dimensionless reduced spin density gradient. And so the C sub j's will be the parameters. We would notice that C0 should just be set equal to 1 to get the uniform electron gas limit correct. But since the functional form itself is not exact, one can always ask, would we be better off allowing C sub 0 to be different than 1? So that's a possibility. And then if we were to do a meta GGA, then these 3 semi-local terms would each have the form of a double power series with a second variable that depends on a dimensionless reduced kinetic energy density at the current point in space entering as well. So that, and so these are the ingredients. These polynomial expansions, well, for argument's sake, we will stop gaining new information as we go higher up in M. So let's say we truncate at M equals 4, and then we consider the fact that each of those parameters could be included, i.e. we would fit it, or allow it to be a floating parameter, or it could be excluded, in which case it's forced to 0. Or it could be constrained. C0 could be set to 1, or C00 could be set to 1 to enforce the uniform electron gas limit. So thinking about 5 parameters for this GGA type expansion in each of 3 power series, you get 2 to the 15th possible functionals, and you can fully search that space. 2 to the 15th is about 100,000. So in fact, that's what we did, is we fully searched that space. The meta GGA, if we truncate at M equals 4, that's 5 terms times 5 is 25 in each expansion. 3 expansions, so 2 to the 75th possible functionals based on including or excluding each of those 75 parameters. That comes out to 10 to the 23rd functionals, which is a number we all recognize as chemists, Avogadro's number. So this is so rich and so complicated that we would call it a functional genome. So the contrast between a GGA and a meta GGA in terms of the complexity of the space of functionals that's represented, it's just an enormous difference. So we will be able to fully search the GGA space, and we can never fully search a meta GGA space. We will do partial searches. If we're going to include exact exchange in the range separated form, this is what it looks like. If we're going to include VV10 or non-local dispersion, it has this general form of a density-density correlation functional, where the kernel that is involved in the double integral asymptotes to an r to the -6 form. All right, so what was the outcome? The outcome was 4 different functionals, and out of roughly a trillion or more that was searched, and 1 of them lives at rung 3, 2 of them live on rung 4, and 1 lives on rung 5. And we did actually search rung 2 as well, but we couldn't substantially beat the best existing rung 2 functional, so we never proposed anything there. So rung 3, that's a meta GGA. It has no non-local exact exchange, and it has VV10 non-local correlation. Rung 5, by the way, then includes PT2 as a descriptor in the non-local correlation. The rank of the search space, well, that's the difference between meta GGAs, which is well beyond Avogadro's number, and something that's based on GGAs, where we can do brute force exhaustive enumeration. And then the question of the parameters. So we were considering the possibility of up to 144 parameters to be included in the meta GGA based forms. But in fact, the protocol, this survival of the most transferable protocol, indicated that we began losing predictive power above about 12 parameters, or 14 in this case. So in fact, we only take a very small fraction of the fitting flexibility that our functional space allows. Even the GGA, we only take 10 of the 16 that we could have allowed. So yeah, so that's interesting. That describes the end result of 5 years of Nabe's PhD research. And let me just give you a sense of how it was done. What you can do in the meta GGA with something like 44 functional, with something like 144 parameters available, is you can search up to 7 free. So that would be 144 choose 7, if you like, that we could just do that. And we began with fixed LSDA orbitals, and then what comes out of that, some 2 billion initial fits, 2 or 3 billion is then the 7 fitted parameters. But what if you want to go further? Well, then you have to force at least 1 parameter to be included, and the And the way we did that was to look for a parameter. So, this is exchange and the different kinds of correlation. And the first thing that we included was something that is linear in the reduced spin density gradient. That occurred in all of the top 10,000 fits of the 3 billion that we initially did. So it seems logical to force its inclusion. We didn't force its value, we forced its inclusion. And then that would allow us to do now 143, choose 7. And then we'd then pick the another parameter that recurs in all of the top fits, which then is linear in the reduced kinetic energy density. And we continue in this way up and up and up in the number of parameters. We could have gone up all the way to 144, but of course you lose predictive power, you overfit. So you also need to make it self-consistent. So we reevaluate orbitals with the best 8 parameters and then reach further. And in the end, that's what led to the 4 functionals that I briefly summarized. To just give you a sense of, well, what comes out of the combinatorial search, how unique is the functional that we pick? This is an important thing to say. It's highly non-unique. This is a plot of RMS predictive power, that is RMS error in prediction, against number of parameters that are included. This is zoomed in highly. So in other words, if we went off the left of the screen and we began with just one parameter, we'd be up around 20 or 30 kilocalories per mole, way off the top of the screen. But as you go 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, the best you can do is going down and down and down, and then it begins to stop and bounce around. And so essentially the idea of picking the functional that has most predictive power, where should you stop? You should stop once this flattens out. And so for argument's sake, we then choose a 12 linear parameter form. But we could have chosen this one instead, or we could have chosen the 13. So in fact, when we pick out a functional and we published it, all we really got was a representative of the fittest functionals. We could have picked thousands of other functionals that would perform nearly identically with subtle differences case by case, but in a statistical sense, nearly identical performance. So the landscape for optimizing these functionals becomes very flat when it comes to the best ones. And of course, there's the gazillion worse ones going way, way up as you pick less and less appropriate parameters. We did this also to make sure that we had functionals that are physically sensible. So we deleted all functionals that, for instance, had negative contributions to the inhomogeneity correction factor for exchange, because the sign of that is definite. We also deleted all functionals that exhibited unacceptable quadrature sensitivity. You've got to be able to integrate the functional for it to be useful. And that's what we did. So now we can assess the performance or discuss a little bit about the numerical performance, and in the process, summarize a little bit about where density functional theory currently is, and I'll speculate a tiny bit about where it might go. Okay, so this is one slide that summarizes a tremendous amount of data, and the way it's done is we actually examined more than 200 density functionals on rungs 1 through 5 of Jacob's ladder, and we're picking out the best one at each rung. And so here we are, the best functional on rung 1. Well, in principle, there's only one functional, but in practice, there are multiple fits to the uniform electron gas. This is the SPW92 fit. And these are the 1 sigma errors. So a 1 sigma error in kilocalories, sorry about the obsolete American units, multiply by 4 or so to put them in SI units of kilojoules per mole. About 2 for non-covalent easy interactions in dimers. Well, a hydrogen bond is 5, so this is a terrible result. We could go to barrier heights. We see 15 kilocalories per mole, 1 sigma error, also a terrible result. That is chemically unacceptable. And so that's our kind of baseline. And then if we go to rung 2, the best functional that we found in testing was Stefan Grimmer's B97-D3 functional, which is just a spectacular improvement over the LSDA, factor of 4 in easy non-covalent dimers, a factor of nearly 10 in easy non-covalent clusters, a factor of 4 in difficult non-covalent interactions, a factor of 2 in isomerization energies that are easy, better in the difficult ones as well, factor of 3 in easy thermochemistry, factor of nearly 3 to 4 in difficult thermochemistry, and a factor of 2 in barrier heights. All the error distributions get narrower. So this is why no one ever runs the LSDA in chemistry, because GGAs cost virtually the same and are simply better. And as I said, when we combinatorially searched the GGA space, we could not substantially improve upon B97. You can do very slightly better, but this was already a good fit, even though it actually used all data in the original fit. At rung 3, our combinatorially designed B97M-RV functional is the best performing functional that we assessed, and the improvements are really useful. In other words, a factor of more than 2 narrowing of the error distribution for barrier heights, not quite a factor of 2 narrowing of the error distribution for easy thermochemistry, factor of 2 or more in easy non-covalent interactions. That's the advantage of VV10 over -D3, slight advantage. And an improvement in isomerization energies. These are becoming, really almost respectable. Although remember, to be 99% confident, you need 3 sigma. So if you multiply these numbers by 3, you still are seeing rather large numbers. So there's more to go. At rung 4, one sees little improvement in non-covalent interactions, except for the difficult self-interaction sensitive ones, which improve by a factor of 2. And the best rung 4 function we tested is our omega B97M-V. We see some improvement in thermochemistry, and then a very big improvement in barrier heights. So barrier heights, difficult non-covalent interactions, these were the highlights here. Chemical accuracy is sometimes said to be 1 kilocalorie per mole. So we're in the ones for a 1 sigma error. So that's not really chemically accurate. But you can see in a statistical sense, steady improvement. And then finally at rung 5, the double hybrid goes slightly below 1 kilocalorie per mole for 1 sigma error in thermochemical bond energies and in barrier heights. So that's quite good. There's no real improvement anywhere else, but there's no degradation either. So in a kind of a statistical sense, we can then say that DFT is systematically improvable. Adding more descriptors and designing carefully gives you statistically better results overall. Of course, there are some functionals that perform worse at rung 3 than the best functional at rung 2, and there are some functionals at rung 4 that perform worse than the best functionals at rung 3. So DFT is systematically improvable if you just inspect the very best functionals at each level. And it could be data set dependent too. But before we talk about that, let's just look at how the best rung 3 functional compares against, well, some other good rung 3 functionals that are not quite as good. And you can see the differences are fairly significant. So in barrier heights, MO6-L and SCAN D3 and TPSS D3 are significantly inferior than B97M-RV. So that's the statistically significant difference. Remember, there are thousands of functionals that are statistically insignificantly different than this functional. So the advantage we gained was simply by being the first group to do this combinatorial design exercise. These other functionals are not combinatorially designed. So that's interesting. And there's kind of a similar story for the global hybrids. Here, well, sorry, these are range separated hybrids and range separated hybrids. This is our 2008 a straight fitted functional, omega B97X-D. It has more parameters. It retains a couple more parameters than the combinatorially designed functional X-V. And you can see there's useful improvements for X-V over X-D across this data, but no improvement in easy thermochemistry or in barrier heights. That's controlled by things that the combinatorial design was not able to improve on. You have to go to the meta level to get better results. And so you can see, for instance, take a fairly recent Minnesota functional, MN15, and compare against omega B97M-V. There's a big gap in non-covalent interaction RMS errors, small gap in barrier heights, notable gap in thermochemistry. So this kind of shows you that the combinatorially designed functional is significantly better than functionals that are designed either by constraint satisfaction or by straight fitting. On the other hand, there are many innumerable unpublished functionals that would perform almost equivalently to this on the same data. All right, one could then go to the data from other groups. So this is data from Stefan Grimmer's group, the quite famous GMTKN55 data set, rungs of Jacob's ladder ordered from right to left, 2, 3, 4, 5, and different data, but broadly similar conclusions. Here is the best functional we saw at rung 2, which is B97-D3. You can see it's very close to the best functional that they identified, RevPBE, and so is in the kind of recommended list. If we go to rung 3, we see that B97M-V or RV significantly outperforms the best functionals that were tested in GMTKN55 originally. SCAN was the best meta GGA. In rung 4, similar conclusions. M-V and X-V, the combinatorially designed functionals, perform slightly but statistically significantly outperform other good hybrid functionals, including earlier omega B97X functionals. And then rung 5 is, if done well, is the best. You can also see this overlap. The worst functionals at rung 3 are worse than the best functionals at rung 2. The worst functionals at rung 4 are worse than the best functional at rung 3. So the statistical improvement is only in the best functional at each level. Okay, so that is more or less that. I want to finish up with some comments about basis set requirements. How do you actually get those good energies? Everything we did in the benchmarking was done at the def2 QZV PP level or PPD level, which is a very large basis set. To what extent do you need it? Well, this is looking at a GGA, PBED3. The error in easy thermochemistry at 631G star against def2 SVPD, against def2 TZV PPD, against def2 QZV PPD, it tells us that density functionals are typically designed, certainly how we design them, to work at the complete basis set limit. If you use a smaller basis set in a statistical sense, your results will be poorer. Well, what if we switch to a hybrid functional like B3-lip? Well, we see a need for at least triple zeta here. Then the need is a factor of 2 reduction in thermochemical errors. Here it was only a 30% reduction. So you could debate whether or not this was essential at the GGA level. You can't debate it at the hybrid functional level. And for a hybrid meta GGA, our new ones, it's much the same. You can only get the very good results we showed for easy thermochemistry if you're at least at the triple zeta level, TZV PPD or TZV PP. And you can see that the error reduction for QZ is slightly larger than was occurring for B3-lip. So the better the functional, in some sense, the more important it is to use a large basis set in order to allow the good properties of that functional to be achieved. all density functionals converge rapidly with basis set in comparison with wave function-based theory. It's nearly exponential in the cardinal number, but essentially the better the functional, the more important it is to be at least at triple zeta level, at least for the relative energies. I can see a question in the chat about geometry optimization. It also benefits from at least triple zeta, but the benefit is smaller because you have better opportunities for error cancellation. Okay, now let's turn to the basis set requirements for non-bonded energies, non-covalent interactions. Let's start off again with PBE-D3, the GGA level theory. And in order to get to the RMS error of 0.46 that it delivers at QZV PPD, you do need at least triple zeta here. Or if you use counterpoise correction, you can get away with slightly smaller basis sets. If you go to the hybrid density functional, then the 1 sigma error in easy non-covalent dimeric interactions shows an even bigger improvement as you reduce the basis set, as you make the basis larger. You now get nearly a factor of 4 reduction in RMS error between DEF2 SVPD and TZV PPD. And if we go to finally the most accurate functional, you see now a factor of 6 error reduction between DEF2 SVPD and DEF2 TZV PPD. So again, the message is unfortunately quite clear that you can never be too rich, too thin, or use too big an atomic orbital basis set when it comes to using a good density functional. So there's not much choice about that. If you are forced by the size of your molecule to go small in basis set, it will impact your errors. Okay, well, that more or less brings me to the end. I'll just make a few concluding remarks and then try and leave some time for questions. So I tried to, in this lecture, give you a general introduction, refresher, review on density functional theory from the point of view of practical performance versus for easy problems. It's worthwhile to say that 95% or so of chemical problems are easy, and that's why DFT is used for maybe 95% of chemical applications. The Jacob's ladder concept is statistically true, and it is worthwhile to use hybrid meta GGAs as the present day workhorse for chemical applications. The combinatorially designed functionals that my group has produced perform very well in a comparative sense. Everything I showed you was for main group containing tests, but additional tests by other groups on transition metal containing molecules are really quite encouraging. I mentioned the MOR 41 and the ROS 79 data and TMC 151 from various different groups. So that's all good, and one can go ahead and do density functional theory with reasonable confidence, subject to the caveats. And the first one is fresh from the previous slide or two, that you really need large basis sets to get the advertised accuracy or to get the accuracy that's been demonstrated. And then even more seriously, you need to have some awareness of when DFT breaks down. In other words, there are failure modes for DFT. And I showed you that very explicitly early on with the delocalization error. So let's just summarize, which is that the most common known failure modes of DFT is the defects of the exchange functional. That's the delocalization error. You should be a little concerned about this whenever you have a system that allows competition between localized and delocalized structures, and you want the localized structure to win. DFT approximate density functionals may favor the delocalized structure. So this is an error often associated with odd electrons or odd holes. Then there is something that I didn't talk about before, but I do want to at least mention in passing, which is density functional theory, at least in the forms that I'm describing it here, is limited in the classes of problems it can do well on, also by what is called the strong correlation error. There are some systems, some molecules that are inherently multi-reference. And when I say inherently, I mean different than pulling apart H2, where some people would say that at long distance, it's multi-reference. Well, no, it isn't, because actually it's two independent hydrogen atoms, so that's not a strong correlation problem. That's why we get such good atomization energies, and why you can run ab initio dynamics. As long as you spin polarize, everything's fine. But strong correlation is where the wave function is inherently multi-configurational, and therefore the idea that we build exchange and correlation from a reference wave function that is just one determinant, well, it's still formally right, but in practice it just won't work very well. And then finally, there may be other problems. I showed you how vast the meta-GGA functional space is, and it's very likely we're not fully constrained by data or by exact conditions, I might add, at the meta-GGA level. It is such a flexible set of descriptors that that it's probably worth revisiting this with more and richer data in the future. Okay, and I will stop there. Thank you very much for listening, and I'm happy to take questions and any discussion. And I'm just looking in the chat now. There's a question from Abhishek about for rung 5. What is the performance of these functionals relative to RPA? The answer is better in general, because in fact the RPA approach is kind of limited by the fact that you take a reference functional, perhaps a rung 2 functional, and then correct it for non-local correlation with RPA. And RPA really is not capable. It has one electron self-interaction error as well. So in general, it does not, the RPA is a powerful way to describe non-local correlation, but adding RPA correlation on top of an existing density functional usually does not outperform a good rung 5 PT2 based functional. As long as for instance, omega B97M parenthesis 2. Let's see. Let me perhaps turn briefly to, there was Abhishek's second question is, for properties such as IPs and EAs and the fundamental gap, what's the performance of these functionals? These are molecular functionals, and they work well for IPs and EAs, but if you carry them into the solid state regime, the performance of range separated hybrids for fundamental gaps is not great, because in fact the asymptotic electron density effect serves to open the gap, make it more Hartree-Fock-like. Question from Ritaj is, yesterday Professor Simons talked about dipole, valence, and correlation-bound molecular anions, metastable states, and used wave function methods. Is there any functional one can use to study these systems using DFT and have suitable accuracy? Your mileage may vary, but range-separated hybrids are not hopeless for dipole-bound states. There's very nice recent work by John Herbert's group, another Q-Chem developer who'll speak later today, I believe, on using DFT to describe the hydrated electron, which is very much in the domain of the kind of states that Professor Simons is talking about. So one can, as I'll talk about a bit later today, one can use density functional theory to describe some kinds of these weakly bound states, as long as range separation is properly included. But But in all things electronic structure, ultimate accuracy belongs to wave function methods. So if you can afford to do wave function theory at the level of coupled cluster, including triples or beyond, one should do it if possible. DFT is not as accurate. And maybe another way to say it is, if we go back to those statistical assessments of error that I presented, they're encouraging in the sense that 1 sigma error at rung 5 finally drops below 1, but 3 sigma is then still not chemically accurate. And so you need some error cancellation for present-day density functional theory to very accurately reproduce exquisitely small energy gaps. We've demonstrated that error cancellation happens beautifully for non-bonded interactions, but it does have failure modes, and if an odd electron is subject to delocalization error or strong correlation error, then we should not expect DFT to be adequate. Let me see. So one other question from Rishab is, if we're already using combinatorially designed functionals, should we add in counterpoise corrections for non-bonded interactions? The answer is yes, please, if you are stuck with basis sets that are not at the basis set limit. Remember, the combinatorially designed functionals are trained at the basis set limit. And at the basis set limit, it doesn't matter whether you counterpoise correct or not. But if you are trying to use a double or triple zeta basis, you'll benefit from removing any BSSE and leaving yourself with any basis set, with only basis set incompleteness error, I guess. Florian's got his hand up.
Yes, I do. Yeah, I have a question regarding the strong correlation errors. Based on the fact that DFT is not actually wave function based, but only uses the orbitals basically as a basis to expand the density. Shouldn't, if we had an accurate DFT functional, the density be still reproduced in the sense that even if we have strongly correlated wave function determinant in the ground state, the DFT orbitals should give an exact averaging of those that exactly represents the actual charge density of the full CI expansion.
Yeah.
So in that case, we shouldn't have any strong correlation errors, or if we had an accurate functional, of course. So I cannot really see directly why there should be such a huge increase in the error due to the strong correlation of DFT.
Okay, well, let me try to give some insight. So you're right that the cone-sham construction remains exact as long as we can find one set of orbitals that make one determinant to represent the non-interacting electron system and get the right density. So in other words, in principle, what you say is right. In practice, though, it's incredibly demanding because the descriptors that we have for exchange and correlation are not subtle enough to be able to typically detect the presence of strong correlation. So it's a limitation of the descriptors and a limitation of the functional form chosen. So if I were to go back to my sort of functional design slide, I would simply say that the functional design is inadequate for strong correlation. There's nothing wrong with DFT, there's nothing wrong with cone-sham theory. I know virtually of no case where the cone-sham construction cannot give you the appropriate electron density, but it's the descriptors. And we don't want an insanely complicated exchange correlation functional. At that point, we should just do wave function theory and try and make sure we get the right answer for the right reasons. So there has been really very, very little progress in addressing strong correlation in a way that is really satisfying within density functional theory. There are double counting problems and all kinds of mess. So you're right in theory, and in practice, everything that is on this slide is correct.
Pardon me for playing devil's advocate here, but doesn't that mean in principle that if the problem is not really with theory itself, but with the application, with the way the functions are constructed and parameterized. Couldn't we also like argue that it could potentially be not a failure of the construction, but actually of the bias or specific databases which are used in the parameterization of the functional, i.e., they are mostly dependent not on systems that typically show strong static correlation, like for example in transition metal complexes.
Well, thank you for the suggestion, for the comment. I think I don't agree. In other words, there are strong correlation cases in the data set that we use for main group systems. And if we were to try and get those cases right, in other words, if we were to put them in the training set, for instance, what we would see is significantly poorer predictive power on cases that DFT should get right. So in fact, the way we trained our functionals was to have no cases in the training set that are strongly correlated, because I feel that we would at best be getting the right answer for the wrong reason. And that happens, we would then pay the price for it later on in terms of reduced transferability. So, so that is a little bit a guess, because we didn't actually try doing what you suggested, but I do suspect it's the case. Anyway, it's a good topic for further discussion.
I think I agree though with the outline presented here. I'm afraid I don't want to monopolize the conversation, but I have one more question, I'm afraid. Is there time for that still?
Yeah, probably if you ask your question and then, but I mean, do bear in mind that Martin, you are returning to us later on, aren't you? So you can, of course, so I'm sure you'll have more questions then. So yeah, one more question and then we will hand over to the next speaker.
The last question is about the 4 types of database characteristics that are used in the parameterization. Personally, I have recently applied DFT functionals for the calculation of hyperfine coupling concept, and I found a very, very poor performance for for transition metals, for the hybrid functionals compared to the non-hybrid functional GGAs here. And the reason seems to me simply that the nuclear structure is rarely, the nuclear electron structure is rarely considered in the construction parameterization of functionals, and the admixture of the hybrid functionals here simply worsens the parameterization of the DFT part for the nuclear core structure.
You could well be right. I don't have enough experience to be sure. So let's just leave it there and hand over to Peter, I think. Thank you for the questions. Those are great.
Great. Thank you again, Martin. That was a really lovely talk.